record. Okay, so hello everyone, welcome to another talk in our webinar series. Oh, sorry, I can hear myself. Let me this off. Okay, sorry. Let me start again. This webinar is also being streamed live on YouTube. You can find a link on our website or access it on our YouTube channel, Linea MCTI. Today we have the honor of having Dr. Diego Pallero,
yeah,
from the Pontificia Universidad Católica de Chile. Dr. Pallero is a postdoc working on galaxy evolution and hydrodynamical simulations. Sorry. His research focuses on the transformations that galaxies undergo in these dense environments, such as galaxy clusters, specializing in the process by which galaxies stop forming stars and the impact that living within these clusters has on these galaxies. Dr. Pallero, thank you so much for being so kind and having accepted to give us a webinar talk today on such an interesting topic. The floor is yours.
Thank you, Tasia, for the invitation. Thank you, everyone, for attending. Well, as Tasia already introduced me, my name is Diego Pallero. I'm currently working in Santiago, Chile. The talk is titled "The Quenching History of Cluster Galaxies in Hydrodynamical Simulations." This is part of my last results. I've been working mainly in understanding the role that the environment have in the evolution of galaxies, particularly concentrated in how clusters seize the star formation of galaxies and how the process of accretion of galaxies into clusters affect their properties. So first of all, I want to tell you what galaxies are. So, as far as I know, as we know, galaxies are agglomerations of dark matter gas stars. We can find them in a variety of shapes and forms. In this image, you can see the tuning form diagram, which is showing the different morphologies and shapes in which we could find galaxies. This image is taken from Spitzer infrared nearby galaxy survey sinks. From left to right, you can see early type galaxies, as we know, these bulgy-like structures, elliptical galaxies, which have little star formation, redder colors, are more metallicity enhanced. Toward the right part of the diagram, you can see these beautiful spiral galaxies, which still undergoing star formation, have these bluish-like colors, these strong spiral arms feature, and that kind of stuff, as some things in between, like lenticular galaxies and more irregular shapes, as you can see here, which are these beautiful as well galaxies. So you can see galaxies in a wide variety of shapes. I'm really interested into understanding how galaxies evolve from one part to another, or how galaxies evolve throughout their history. This is not an evolutionary diagram, but you can see like different stages actually of galaxy evolution within this picture. So I've talked a lot about the environment of a galaxy. I like to define the environment of a galaxy as the place in the universe in which a galaxy resides, and the information about the companionship of those galaxies. So in the universe, we can find galaxies in isolation, or like this beautiful spirally ring galaxy here, NGC 1398. We could see galaxies merging, like if they have a companion and they undergo this kind of fusion between of them, like the antennae galaxies you can see here in the second panel. We can find galaxies in compact groups or groups of galaxies, which are association from 3 to 5 galaxies, which are expected to be merged in the future as one big structure. Here you can see the Stefan Quintet, a beautiful compact group, AGC 92. But for me, at least, one of the most interesting things to study in galaxy associations are galaxy clusters, which are the most massive visualized structures in the universe. They comprise from hundreds to thousands of galaxies, all interacting with each other, at least gravitationally. And within these kind of structures, all the environmental mechanisms that you could expect to affect a galaxy is happening. So they're really entertaining to understand because you can see from gravitational interactions to hydrodynamical interactions. You can see galaxies merging with each other. You can see galaxies interacting with the intra-cluster medium of the cluster, like the gas component of the cluster itself. So you have a lot of different mechanisms that are happening at the same time. So the difficult part and the entertaining part, at least for me, is trying to disentangle each one of these mechanisms and trying to understand which one dominates over the others. So it is known from around 1980 that the morphology of the galaxy or the shape that the galaxy have is also related with the environment in which the galaxy resides. This plot here is taken from Católica de Chile 2003. In this paper, they using data from Sloan Digital Sky Survey, try to show this dependence of the morphology of the galaxy with the environment in which a galaxy resides. So, for example, here in the left panel, you have the fraction of early to late type galaxies. Early galaxies are like this most elliptical kind of shape. Late type galaxies are these disky-like structures as a function of, for example, cluster-centric distance. So the distance to the cluster center. As you can see here, late disks usually their fraction decreases toward cluster centers, and on the other hand, the early type structures, the fraction tend to grow toward cluster center. This result is even more clear when we took into consideration galaxy density instead of the cluster centric distance. So you can see here that late disks tend to decrease in fraction towards more dense regions, and on the other hand, early type galaxies tend to grow in fraction toward more dense regions. So what this is showing is that the properties of galaxies are related with the environment in which galaxy resides, but how? That's the question. How it depends and why it depends, right? So I like to think that the 5 most important processes that could be affecting galaxy evolution, in the sense of the environmental mechanisms that could be affecting galaxy evolution, could be summarized in these 5 huge different processes. We have first tidal interactions, which are only gravitational interactions that could affect, for example, the distribution of baryons within galaxies. This happens a lot within galaxy clusters because, well, galaxy clusters are the most massive structures, visualized massive structures in the universe. As we have a lot of galaxies, galaxy encounters is pretty common. It's not like the galaxies will merge or fuse like completely because of the high velocity dispersion that galaxies have within clusters, but aggressive encounters could happen and happens a lot. It is known as galaxy harassment. We have as well a hydrodynamical interaction between the gaseous component of clusters and the gaseous component of galaxies in the form of run pressure. So run pressure is a process in which galaxies, in the accretion process within the cluster, the hydrodynamical medium, like the gas component of the cluster, tend to stop the gas component of the galaxy and removes the gaseous component of the galaxy. So as galaxies doesn't have more reservoirs to keep forming stars, they cease their star formation in a process we know as quenching. If this stripping of the gas is not high enough to remove all the gas in the galaxy, but only removes the hot gaseous component of the galaxy enter in a process of observation in which slowly starts to consume the remaining gas and subsequently stop their star formation. And all the processes that I mentioned before would also take place before their accretion into the clusters if the galaxy comes in another substructure, such massive galaxy groups, or in another cluster, or in these compact groups that I showed before. All those processes are usually referred as pre-processing. In this representation of the different process that this is a clear representation of the different process that could be affecting the galaxy evolution, made by the Dr. Ari Shunk from Yonsei University. So here you can see, for example, harassment, which are these aggressive galaxy-galaxy encounters that could, for example, stop the star formation or hit the varying component of the galaxy, or more classic galaxy encounters, repression stripping, so on and so forth. So there are different ways of study galaxy evolution, and in particular the impact of the environment in galaxy history. The way in which I confront this problem is through hydrodynamical simulations. Hydrodynamical simulations are galaxy formation models, numerical models in which all the physics that we know is put in the computation and help us to understand the evolution and the collapse of structures in a way that we weren't able before. In this movie that you're seeing right now, you can see a small volume from the Eagle simulation. And you can see the evolution of structures throughout time. In the upper left panel, you see the evolution of all the components. In the upper right panel, you see the evolution and collapse of dark matter. Lower left, you see the evolution of stars, and lower right, you see the evolution of gas. I'm gonna put the movie again just to see, just for you to see. So one of the key advantages that we have in hydrodynamical simulations is that we not only know the properties of galaxies, the properties of structures at given times, but that also we can see the evolution of these galaxies and their properties throughout time. So for example, we could take the galaxies within a cluster and we could disentangle their evolution using different properties to understand what are the physical mechanisms that are affecting them. So, for example, we could select galaxy clusters from the Eagle simulation. We could take the galaxies, the satellite galaxies of those clusters. We could follow them in time and see in which part of their evolution their star formation stopped. And actually, that's what we did. In this talk, I will be, and the results presented in this talk, I will be using two different simulations. The first one are the Eagle simulations. It's a 100 megaparsec box, full physics hydrodynamical simulations with a mass resolution from around 10 to the 6. So we are able to resolve galaxies as small as 10 to the 8 solar masses, which we enter in the dwarfish kind of regime. The great thing about Eagle simulations is that there are many properties that are well resolved within the simulation and actually are well matched with observations. So in a way, we could make sure that the things that we are understanding from these galaxies could also be replicated in observations. That's great about Eagle simulations. The only bad thing about the simulations, well, the two bad things about the simulations is that the first one, we don't have many clusters because as we have only an 100 megaparsec box, we could only resolve 10 clusters within simulations. And the clusters are not that massive, actually. The most massive structures that we could find them, they find there from around 6 times 10 to 14 solar masses, so are between the low to middle mass regime, at least for galaxy clusters, I mean. And the other not so great thing about the simulation is the temporal resolution, which is from around a giga-year. So there's a lot of different things that we're missing in between this time resolution. So to fix that issue, we are using as well the Cluster Eagle project, which are zoom-in simulations, which uses also the same galaxy formation model than the previous simulation. So in a sense, the properties of galaxies are directly comparable because it's not dependent on the model, at least for comparison between results. And as this is a zoom-in simulation, we were able to select much more massive clusters. Actually, in the simulations, we have 30 galaxy clusters from the low mass regime, around 10 to the 14 solar masses, up to the most massive structures that we know, like coma-like clusters like 0. in the mass range of 10 to the 15.4, and so temporal resolution actually is better as well. It's from 500 megayears or more or less in temporal resolution. There are a lot of processes that we are not able to resolve yet, but it's much better than we had before. And we have clusters with a high resolution simulated up to 10 bit already, so we can follow the evolution of galaxies from the outskirts of clusters toward the most inner part of clusters, which is great. So in a sense, this talk will be split between two sets of results. The first one related to the Eagle simulation, and the second one related to this cluster Eagle simulation. So as I mentioned before, in the first part, I will be tracing the quenching evolution of these galaxies in the Eagle simulation. For that, we try to characterize key moments in galaxy evolution for all the satellites within 1 bit radius of the clusters. The first moment in which we were interested is the moment when a galaxy suffered their strongest drop in star formation. So in this plot here, you can see the evolution of the star formation rate, like star formation history of a galaxy as a function of time. And the little blue stars that you can see here is the moment that we select as when the galaxy suffered their strongest drop. So is the normalized strongest drop between two consecutive snapshots. And as you can see here, the galaxy, something happened in the history of galaxies here that, make it drop their star formation like dramatically. Interestingly here, this drop in star formation, this drop in star formation also is related with the moment when the growth in stellar mass of the galaxy tend to be like slower dramatically as well. In this panel, you can see the evolution of the star, the cumulative growth of the stellar mass of the galaxy as a function of redshift. So apparently, galaxies suffer this strong drop in star formation rate. Their growth in stellar mass tend to be not completely stopped, but the growth is like dramatically slower after this moment. And the other moment that we define that would be important for the galaxy would be when it crosses a particular threshold of our choice in specific star formation rate. I say in our of our choice, but it's a threshold used by different authors, such as in Wetzel et al. 2012 and 13, it was in 2010 and 12 as well. And this threshold in specific star formation rate is 10 to the minus 11 solar masses per year. And what we can see here is that once that the galaxy crosses this threshold in a specific star formation rate, they usually stop completely the star formation rate. And an interesting thing here is that this blue dashed line that you can see here is the moment when the galaxy crosses the virial radius of a cluster for the first time. So that would be key in the future. So first, regarding the strongest drop in selection criterion to define galaxies, we define that galaxies that suffered, when the galaxies suffer this strong drop in star formation rate would be the moment when we refer to them as processed. In the literature, usually they refer to preprocessing to a lot of different things. Some refer to the preprocessing as the moment when galaxies cease their star formation. Others when the galaxy start to stop the star formation. Some people even call galaxies as preprocessed if they show redder colors than what they should have, and doesn't use any particular definition of star formation rate. But for our convenience, we define the processing time or the pre-processing time if the galaxy suffered these strong drops in star formation rate outside the cluster, while not bound to the cluster, like as they are bound to a different substructure. So in this plot here, you can see the normalized fraction of the strongest drop in the star formation rate as a function of redshift. Blue dots correspond to galaxies that suffer this strong drop outside the cluster, and the red dots are the ones that suffer these strong drops while bound to the main structure, to the main cluster. Each panel hill corresponds to one particular mass bin of the cluster masses. And as you can see here, there are no particular relation between redshift and nor the strongest drop to take place, or the how strong was the drop. So there are no relation with redshift in any sense. But also we can see here that most of the galaxies that we can see in cluster at present day were pre-processed, like suffered this strong drop transformation before they were accreted into the cluster. But to see if this strong drop actually have something to do with the environment in which the galaxy resides, we look for the host halo mass in which these galaxies suffer these strong drops, just to see if these strong drops happen in the mass of groups of galaxies, or in isolation, or in compact groups, or that kind of stuff. So in these histograms here, you can see the properties of the galaxies at the time of the strongest drop. In the A column that you can see here corresponds to the mass of the host in which the galaxies were residing at the time of the strongest drop. The total mass of the galaxies, including gas, stars, and dark matter. The ratio between the stellar component and the total mass of the galaxy, just to see if they are more dark matter dominated or more baryonic dominated. And the stellar mass of the galaxy, their inflow time. The inflow time is defined as the first time that the galaxy crosses the virial radii of the cluster for the first time. And as you can see here, at least for the host halo mass, we don't have any particular relation with the mass. Each bar, the color of the bars correspond to a different kind of population. The red ones are galaxies that were processed or suffered the strongest drop within the cluster virial radii. The blue bars here correspond to galaxies that suffered these strong drops while being satellites of another halo, and the green bars here correspond to galaxies that suffered these strong drops while being central galaxies. And as you can see here, galaxies that suffer strong drops, centrals usually are low mass galaxies inhabit low mass halos, so mainly in isolation, and correspond to a completely different population of galaxies, are usually quite dark matter dominated. Are usually quite dark matter dominated, but are a completely different kind of population. But besides those satellites, the distribution for host mass at the time or the strongest drop is quite broad. So this kind of shows that the preprocessing as we define doesn't have much to do with the environment of a galaxy. But what is interesting is that the mass, stellar mass of the galaxy at the time of infall, it's really different from those that suffer the strongest drop within the cluster and the ones that suffer the strongest drop outside the cluster, regardless of if they are satellites or centrals. So apparently more stellar-dominated galaxies usually suffer these strong drops in star formation or are processed within the cluster that we are studying, contrary to those that are less baryonic matter dominated, which are more susceptible to these changes in sudden changes in star formation rate. But if we use a specific threshold and specific star formation rate, select galaxies as quench or not quench, the results actually change a lot. in these histograms here, you can see, well, the host mass at the time when the galaxy reaches this threshold in a specific star formation rate for the first time, the mass of the galaxy, how baryonic dominated are, the difference between the time of the quenching and the time of the inflow, in which I remember you that the time of the inflow here is defined as the moment when the galaxy crosses the virial radius of the cluster for the first time. But yeah, what is really interesting here is that, contrary to what we found for the pre-processed population or the processing or these strong drops, the quenching time, so when the galaxy crosses this threshold in specific star formation rate, usually take place in, I'm sorry, here, usually take place in massive groups of galaxies or galaxy clusters, just from the mass of the host at this time, regardless of if the galaxy was quenched within the same structures that we are studying, represented here by the red bars, or as a satellite of a different structure, represented here by these blue bars. And doesn't have much to do with the mass of the galaxy, as we can see here from the B column. There are no large difference between the different populations of satellite central, satellite frequench or central frequench, or galaxies quench within the same cluster. Like we cannot see large difference between the different population of the galaxies. It's more like it have to do with the environment, with the mass of the galaxy. And something interesting is that the 95% of the galaxies in our sample suffer these strong drops in star formation rate before they suffer their quenching time. So apparently it's like a two-stage kind of evolution in which galaxies in any host halo, in any kind of host halo, suffer these strong drops in star formation rate, but keep forming stars for a little longer. And once that they reach these massive like structures, like massive galaxy groups or galaxy clusters, their star formation is completely stopped. So to characterize these kinds of results, in this plot here, you can see the growth of the quenching fraction for the 10 clusters that we select from the Eagle simulation as a function of their accretion time. Negative values here correspond to the times when to the moments that the galaxies outside the cluster. Positive values here correspond to the moments when the galaxy were inside the cluster. And 0 here represents the moment when the galaxy crosses the virial radius for the first time. So as you can see, around 4 gigayears after galaxies crosses the virial radius of a cluster, they usually get quenched. There are a relation in here between the pre-quench fraction with the cluster mass. Lines are color-coded by the cluster mass at rate of 0. And you can see here that most massive clusters tend to have higher fraction of pre-quenching in contrast to these low mass clusters. So around between 20 and 60% of the galaxies in our sample arrive as quench into the cluster. So the question is why this large fraction of galaxies arrives as quench galaxies to massive clusters. And when we study the kinds of mass that most massive galaxy clusters are accreting, we found that massive clusters usually accrete more massive structures as well. In these histograms here, you can see the kind of halos that galaxy clusters are accreting as a function of their mass at rate of 0. Each row here represents particular mass spin for the cluster mass. And as you can see here, that most massive clusters showed in the upper row usually accrete more massive structures as well. So in these kind of massive groups or low mass clusters, most of the galaxies are suffering environmental effects, quenching their star formation, and once that they are accreted into the cluster that we are studying, they already underwent all their evolution, to say in a way. So apparently, from what we could see here, the pre-processing and the pre-quenching of galaxies is more related with the environment in which a galaxy resides before their accretion than to the mass of the galaxy itself. So apparently, for the galaxies that we could see at redshift 0 inside galaxy cluster, the environment is more important than the inner quenching. This result is part of the hierarchical nature in which the universe is constructed. So it's a direct consequence of the cosmology itself. Those are the main conclusions of the first part of the project. I will come to them like at the end. And for the second part, we were trying to understand which one was the main mechanism behind the quenching that we were finding in the first part. So first of all, we wanted to understand at which mass we could see this change in the population that dominates within galaxy clusters between the quenching of the galaxies within the same structures that we are studying and the pre-quenching that we were finding toward more massive structures. And in this plot here, you can see how the dominant population changes with cluster mass. And you can see that from around here, from around 10 to the 14.6 solar masses, the dominant population tends to change. So if we're studying cluster more massive that, let's say, 5 times into the 14, usually more than 50% of the population suffers some kind of environmental mechanism that sees their star formation outside the cluster that we are studying. But if we're looking at cluster less massive than them, at redshift 0 at least, the majority of its population were quenched within the same structure. So all the environmental mechanism that produces the quenching of the star formation happened within this same cluster. These results change if we look clusters at different redshifts. Interestingly, if we look toward higher redshifts, the fraction of pre-quenching drops up to 0 even, and all the galaxies within that cluster suffer environmental their quenching within the same structure that we're studying. In this plot over here, you can see the evolution of some properties such as the stellar mass of the galaxy and the host mass in which the galaxy galaxies got quenched as a function of the cluster mass, and color coded by the fraction that each population represents. Dots correspond to the in situ population, and the squares correspond to the pre-quench population. So what we can see here is that at low redshift, most galaxies got quenching halos of around 10 to the 14 solar masses, so low mass galaxy clusters, regardless of the cluster mass. But as we go toward higher redshift, most of the galaxies got quenched within the same structure. So the mass of quenching would be the mass of the cluster that we are seeing. And this mainly happens because galaxies doesn't have the time to be in a different structure than the cluster that we are seeing. So these massive clusters or low mass cluster, actually a low mass cluster would be as well, at high redshift are the first massive structure, the first dense structure that galaxies are encountering. So in a way, this result shows that galaxies get quenched in the first massive halo that they experience, regardless of the cluster mass. If we have massive groups, that would be the structure in which the galaxy will get quenched. Is the first time that the galaxy spends in a dense environment is a massive galaxy cluster. In that cluster would be their quenching. And from this simulation, as we have better temporal resolution and we have more massive clusters, the same plot that we saw before of the evolution of the quench fraction as a function of the accretion time, the results after their crossing of the virial radius of the cluster for the first time are much more clear. In these coma-like structures, these really massive structures that we can see here, up to 80% of their population was already quenched before the accretion into the cluster. So, for example, from thousands of galaxies that we could see in these massive coma-like clusters, up to 800 of those galaxies were quenched in a different phase, and only a few were quenched within the same cluster. But if we go to these low mass clusters, such as Fornax, for example, most of its population probably underwent developmental effects within the cluster. They don't have that large fraction of pre-processing. Obviously, talking about percentages, not that in Fornax you do not have pre-processing or galaxies undergoing pre-processing. It's just that most of the galaxies are suffering environmental effects due to the cluster itself. If we see these results at different redshifts, we could see that if we go, for example, at redshift 1, regardless of the cluster mass, as I said before, galaxies suffer their quenching within the same structure. As you can see in the upper left panel, the quench fraction before their accretion time showed here by 0, it's nearly null, but once that they cross the virial radius of the cluster for the first time, these quench fractions rapidly grow from 0 up to 70% in some times, which is a lot in a really short time scale. I mean, I'm talking about 1 giga-year or so, 2 giga-years of most cases, which is typically the time that a galaxy takes from the outskirts of the cluster toward the center. And these results become much clearer as we go to lower redshift. This outline here, I'm sure that you're wondering why it's so weird, is because underwent a major merger, like a bullet-like merger at low redshift. So that's why it has this large fraction of pre-quenching. But something that caught our eye at this point is what's so special about this video already that showed this large fraction of pre-quenching after crossing it, right? Why they're so special? And in 2019, an article by Ian Roberts showed that apparently there were a particular threshold in density of the intercluster medium in which quenching started to be more efficient. The density threshold is around 10 to the minus 28.3 grams per cubic centimeter. In these plots here, you can see the quench fraction as a function of the density of the intercluster medium for different kinds of galaxies, and low mass galaxies show this change, this sudden change in the slope at this particular threshold. And interestingly, in our simulations, this specific threshold in the intercluster medium is reached the virial radius of the cluster, even for low mass clusters. So apparently, it should be noted that the clustering simulation tend to have slightly denser gas density profiles for the intracluster medium. It's around 2 times denser than what you find in observations. So in a sense, we could be finding this sudden change in the slope of the growth of the quench fraction due to this increase in the density value, just up to a factor of 2. But the interesting thing here is that we recovered the same threshold that they recovered in the article using all the observations from Chandra and the Sloan digital size survey. So that's really interesting. If we look at the particular density in which galaxies got quenched regardless of their condition regardless of their condition of frequent or in situ quench, we found that most of the galaxy got quenched at densities higher than the threshold proposed by the authors. So if we have that the density, we found this particular threshold in density, and we found that the particular quenching time is once that the galaxy crosses the virial radius first time. The last question that we wanted to ask was, what is the main mechanism? What is the main culprit behind this satellite quenching? So we measured the ramp pressure of galaxies at the quenching time. We defined that galaxies will be ramp pressure dominated if the ramp pressure, etc., of the galaxy is greater than the resonant force of the galaxy. And really interestingly here, we found that the growth of the fraction of ramp pressure dominated galaxies for satellites in clusters, it followed practically the same distribution that the growth of the quenching fraction for the same galaxies. So apparently, once that galaxies cross the virial radius of a cluster for the first time, they rapidly get ramp pressure dominated in a time scale of less than 1 gigayear. They got quenched as well. So at least from the Eagle simulations, we learned that around 80% of the galaxies within clusters got quenched because of ramp pressure. And that this usually took place in halos from around 10 to the 13.8 to 10 to the 14.2, which is the mass of really massive galaxy groups or low mass galaxy clusters. So finally, on the main conclusions of the talk, the thing that I want to use to understand from my study is that if you're interested in environmental mechanisms, you have two paths to follow, at least from what I learned from simulations. If you're interested into study the environmental mechanism taking place, you could study or low mass clusters at low redshift or clusters at high redshift regardless of the mass, because most of the galaxies that are inside those kind of structures are undergoing all environmental effects at that time, or experience their environmental effects within the same structure. But if you're interested in pre-processing or pre-quenching or to select galaxies that underwent this kind of phenomena outside the cluster that you're seeing, it's easier to go to low redshift and study massive clusters, because most of their assembly is due to the accretion of already passing galaxies. And that ramp pressure apparently is the main culprit behind the satellite quenching from clusters as we study. And that usually galaxies before their accretion into the structure that we're seeing suffer strong drops in their star formation in any kind of halo. So these strong drops in star formation apparently are not related with the environment itself. As a comment, I look for the moment of these strong drops in the star formation rate, and usually took place because of starburst at intermediate high redshift, or to a galaxy merger that produced sudden burst in star formation and then acquiescent star formation after. And for the future steps, from the work that I did, like the projection of this work, is trying to characterize time scale in which other properties besides the star formation change, such as metallicity, color. Because in 2013, Wetzel proposed a scenario in which galaxies quench in two stages. Like first, slow quenching, in which galaxies start to change properties such as metallicity and color. And once that they enter the cluster, they suffer a rapid quenching in a small time scale from around 0.8 gigayears or so. So in our work, we were able to characterize this rapid quenching, to find the mechanisms behind this rapid quenching, but we're not sure if this slow quenching happens as well. So we're interested in to study the timescale in which these other properties as well change. We're also interested in to study what is happening in the outskirts of clusters. In Baje et al. 2013, he shows that run pressure turbine could be efficient up to 5 virial radius of the cluster. But we're finding that once the galaxy crosses the virial radius of the cluster for the first time, the run pressure start to take place, become more dominant than the restoring force of the galaxy, and rapidly got quenched. So what is happening between this 1 and 5 virial radius of the cluster? Using our simulations, we would be able to disentangle the different processes that's happening in this regime as well. Also, we want to compare with observations, using, for example, different criteria of several properties such as metallicity, color, morphology, the position in phase space. Maybe we would be able to split between the pre-quench population and the in-situ quench population, and to learn more about these kind of galaxies from observation. That would be our next goal, actually. And we are also trying to make high resolution simulations with high temporal counts in order to better constrain the time scale in which each of these processes is taking place. So thank you again for the opportunity. Thank you for the time. Happy to hear all your questions.
Thank you so much, Diego. Thank you so much for the interesting talk. So now we have time for questions from the audience. Please raise your hand if you want to ask a question. If you're on YouTube, you can type the question in, and I'll read it out to our speaker. Let me just check YouTube very quickly. In the meantime, we can take questions from the audience. Okay, I guess I'll start asking the first question. Diego, can you please go back a few slides? You explained this very quickly, but I didn't understand. It's the SSFR threshold criteria. It's the one where you had like C's.
Which one, sorry?
No, is that? It's no, that no, it was after that. SSFR threshold criterion. So you had a plot with different colors. No, not that one. No. Yeah, this one. So can you please explain again what the C's are? The sorry, different color. What C1, C2, yeah.
Okay, sorry. Yeah, each line corresponds to one cluster in the Eagle simulation. So those are like the numbers to find them, like the idea of the group memory if you want to find them in the simulation. So here each line represents the growth of the quench fraction of one particular cluster within the simulation, and are color coded by their mass at rigid zero. So for example, these red clusters here correspond to the most massive clusters in the simulation, and the blue ones here correspond to the least massive clusters in the simulation. And the y-axis shows the growth of the quench fraction from as a function of the accretion time. So we are seeing the behavior of galaxies 4 gigayears before their accretion up to 4 gigayears after their accretion. So what I want to show you here is that 4 gigayears, for example, after galaxies were accreted into the cluster that we're studying, the quench fraction tend to be much lower. Like most of those galaxies are still forming stars even 4 gigayears after their accretion. But once that galaxies crosses the virial radii of the cluster for the first time, they rapidly get quenched, and we can see this incremental in the quench fraction. And after 4 gigayears, most of its galaxies have already get quenched It's a normalized time scale. Like for each galaxy, I measure the time in which the accretion take time. The time of accretion, and see how that galaxy is 4 giga year before and 4 giga year after. Just to see like in which time scale the environment is affecting that galaxy. Is clearer, I think, here, which is practically the same plot, but for the other simulation, which we have like more clusters, and these bluish lines represent least massive clusters, and redder lines correspond to most massive clusters.
Okay, thank you. I have another question, but we have a question in the chat from Rodrigo. He's asking if you have any plans on working with LSST data.
Actually, yes, that would be amazing. The thing about the thing about the selection criteria that I want to develop is to apply it to, for example, LSST. I was thinking, and actually that's rather exploratory, but what I want to do is to measure the well, color metallicity, phase space, for example. I'm thinking that with LSST we don't have LSST information, but we have photometry for at least 5 filters. So there's a lot of properties and color combinations that we could test in order to split between galaxies that were pre-quench and in situ quench. And at least I think that galaxies that got pre-quenched probably have different metallicity than the galaxies that got quenched within the same cluster, because they have different star formation histories and different assembly histories. So what I want to do is to check in the detail those properties and to select the best combination of properties to split between samples, and that's try to apply it, for example, to LSST. I want to test it with Sloan. I want to test it with S+ as well, because as we have like different filters and a lot, we could make a lot of different combinations to see the better properties split between pre-quench population and in situ quench population, especially for these massive like structures. For example, for coma, would be really interesting to try to split between populations.
Rodrigo is okay. Rodrigo says thanks. So I have another very I don't know how basic this question is, but so you have the SPS model, right, for your galaxy, and then basically what you're saying is that for quenched galaxies you would have to have a different model because these properties are going to be different. Is that? I mean, am I thinking about this right?
Yeah, no, I think not, because as these are hydrodynamical simulations, it's like you have all the physics for all the galaxies. And you make the simulation from redshift, for example, 100, and let the universe evolve up to redshift 0, all with the same conditions. But the properties of those galaxies as a consequence of the galaxy formation model implemented like from the start. So I'm taking I'm selecting galaxies by the properties once that they already evolved, so they all evolve based on the same galaxy formation model. So in that sense, the properties of these galaxies are not a consequence of the model itself, to say. I'm not sure if I understand your question. Maybe I didn't understand it.
Yeah, because I just started working with galaxies, so I'm thinking about the galaxy models in that way. Like if I'm looking at if I'm taking observations, is it am I right to model both galaxies with the same I mean using the same SPS model, or do I have to make another consideration for quenched?
Yeah, I don't think so. I don't think so, but I may be wrong, but I don't think so.
Okay, no, this is good because then it would be more complicated. So there's another plot. Okay, no, actually there's a raised hand. Marcelo, go ahead, please. Otherwise, I'll just hug you, Diego. Go ahead.
Okay, can you hear me?
Yeah.
Nice. Hi, Diego. Thank you very much for your very interesting talk and very nice work. According to your results, it seems that preprocessing has a very large contribution in quenching galaxies. And my question is, if you know something about what are the main mechanisms that drives the quenching as preprocessing? So when the galaxy before infall, what are the main mechanisms of quenching in the galaxies?
Yeah, yeah, sure. Thanks for the question. At least for pre-processing, as I defined it, like these strong drops in star formation, the main mechanism was sudden starbursts and mergers of galaxies, for what I found in Eagle. For the pre-quenching, like those galaxies, for example, all these population in here of quench galaxies that got this quenching state before their accretion into the cluster, what I found is that is run pressure as well. It's just that in these massive structures like coma, most of the assembly of their galaxies was by accretion of another clusters or massive groups. So galaxies underwent run pressure in that group, right? It's like what I wanted to say is for a cluster like coma was formed by the merger of different clusters and groups at different redshifts. The galaxies accreted within these groups were already quenched within that group. And the process behind that quenching was run pressure as well. Is that they are accreting structures with intercluster medium dense enough to quench the star formation of those galaxies. It should be noted as well that in the simulation, we're resolving galaxies up to 10 to the 8 solar masses. So most of our galaxies is comprised by this dwarfish-like system. So in a way, it's easier to quench those structures. If we go towards more massive galaxies, the results change a little, but not much. Still run pressure, the main mechanism, at least for galaxies from most massive than 5 times 10 to the 9 solar masses.
Okay. Another question, maybe related, maybe you said about this and I'm not remembering, but did you compare at different redshifts what happened if, when preprocessing is happening? Because what I'm thinking here is when we go to higher redshifts, we have the protocluster stage and these subhalos that will turn up to a cluster in the future. They are not the massive for some kind of mechanism, for example, as run pressure stripping. So for me, what I would expect as a higher redshifts, these pre-processing are lower, and maybe when with time this starts to become a main contributor.
Yes. Yeah, totally true. In this plot, I showed results up to redshift 0.9, which are mostly clusters already. But actually, I went with this plot up to redshift 3 just to see the contribution of protoclusters and that kind of stuff. As you mentioned, when we go towards higher redshifts, like for example redshift 2 or 3, the pre-quench fraction drops to 0. The results shift towards more time the galaxy should spend within cluster, because yeah, the intercluster medium is not totally collapsed, so we don't have these dense structures to quench its formation. So once that the run pressure become less efficient, the quench fraction actually drops as well, and the pre-quench fraction drops dramatically.
Yeah, perfect. Thank you.
Thank you.
Okay, we're a little bit over time. Do we have any more questions? Okay, Diego, can I ask you another quick question before before we wrap up? Can you go to? So actually, I can talk about this plot as well. So there's no, you mentioned the outlier here, right?
Yes.
Is that at redshift equal to 0? Is it an outlier also at Z, the redshift equal to 0.54? So is that the same thing?
Yes.
Is it because of the mergers as well? Okay.
Yes.
Oh, it's also the same one. Okay. Okay, I was just wondering if there was going to be a difference because of the different redshifts. Okay, so let me just check YouTube very quickly again to see if we have any more questions. No more questions on YouTube. Okay, then I think we can wrap this up. This presentation will be available on our website and on Linea's YouTube channel. Thank you everyone for attending, and a special thanks to you, Diego. So I hope everyone have a great day, stay safe, and I hope to see everyone again for the next webinar. Thank you so much.
Thank you, everyone. See ya.
Bye-bye.